I've got a problem up here on the board for you folks to try. I'm giving you a function f of three variables, e to the xy times cosine of yz. And then I'm giving you a vector function t that maps us into 3 space. Okay. What I want you to do is find the derivative of this composition, f of r of t, and I want you to do it using the chain rule for functions of more than one variable. Okay. So pause the video, give that a shot, and then tune back in and we'll work through it together. Welcome back. Okay, so I'm going to draw myself a diagram here. So basically this function of 3 variables would be spitting out a w value. Okay. So w depends on 3 things. It depends on x and on y and on z. But each one of those, because this is just my x, this is my y, and this is my z, so each one of those in turn just depends on t. Now, of course, it's the same t, so I could, if I really wanted to, just write the t once and have a diagram that looked like so. But you can see it starts to get a little bit crowded in here. And so my preference is to just write it once for each thing that depends on it. Okay, so now on my diagram, every time there's one of these lines connecting variables, that says there's a dependence relationship between those variables, and so there's going to be a corresponding derivative to measure the rate of change. So up here, w has 3 lines leading from it, so it depends on 3 variables, so those derivatives are going to be partials. So we'll have the partial of w with respect to x, the partial of w with respect to y, and the partial of w with respect to z. And if I preferred, since w is f of x, y, z, I could be writing these as the partials of f with respect to x, y, and z. Just a matter of personal preference at this point. All right, down here, each of these depends on just one variable, so these are going to be full derivatives. So that's x prime of t, y prime of t, and z prime of t. Okay. And then, to get the derivative of w with respect to t, and that will be a full derivative, because ultimately, we've got just one variable down here on the bottom. So we're saying w is a function of just one variable. And this is equivalent to the full derivative of f of r of t. All I do is multiply the derivatives along each path that connects w to t and add together those results. So we'll have the partial of w with respect to x times x prime of t. That's the product of these derivatives. Plus the partial of w with respect to y times y prime of t. That's the product of the derivatives along this path that connects w to t. Plus the partial of w with respect to z times z prime of t. That's the product along this path that connects w to t. Okay. Now, I find the simplest way of remembering this is to simply use this diagram. Okay. If you prefer not to use the diagram, you could also remember that this is actually just a dot product. This is equivalent to the gradient of f dotted with r prime of t, because that would of course just be the partial of f with respect to x, partial of f with respect to y, partial of f with respect to z. There I'm using f's just because I had written f here, but f gives out my w values. So that's these 3 functions right here, dotted with x prime of t, y prime of t, z prime of t. So if you want to show me that you're getting the result using chain rule for functions of more than one variable, either draw the diagram or write out that you're using the dot product. Either is correct. I just don't want you actually writing out what the composition is and skipping all of the multivariable stuff. Okay, excellent. So now I want to just write out what these things are. Okay. So here we're taking the partial of this with respect to x. Well, that's kind of nice because the cosine of yz then is just a constant. So the partial of this would be y times e to the xy, and then times cosine of yz. We've got to multiply that by x prime of t. X was t squared, so that's going to be times a 2t. Plus, now I need the partial of w with respect to y. Now that one is going to involve product rule because y shows up in both of these factors. So I'm going to immediately just put some brackets there so that I remember that that whole thing will get multiplied by y prime of t. So the partial of that first factor with respect to y is just x e to the xy, and that's times cosine of yz, plus first factor of e to the xy, times the derivative of cosine of yz. That's going to give me a negative. So I'm just going to change that to a negative sign right there. That's going to give me a negative sine of yz times the partial of yz with respect to y would be a z. I think I'm going to write the z at the very front. So we'll get, net result is negative z times e to the xy times sine of yz. That is the partial of w with respect to y. Y prime, let's see, we've got e to the 3t, so that's just going to be 3 e to the 3t. Plus partial of w with respect to z. Well, here I don't need product rule because there are no z's in that first factor. Okay, so we will have a negative because we're taking the derivative of cosine. Okay, so we're going to have an e to the xy because that's constant, sine of yz times the partial of that with respect to z would just give me an extra factor of y. And then I've got to multiply that by z prime of t, which is just going to be the reciprocal of t. So that's going to give me times, let's see if I can fit this in here, times a 1 over t. Oh my goodness. Okay. So this is an intermediate step because at this point I've got all my variables. In my final answer, I need to remember that I want to be evaluating these guys at t, so that the only variable that shows up in my final answer is the one that's on that bottom level. Okay. So now I'm just going to go through, I'm going to sort of slide things to the left since I'm running out of space here. So y e to the xy, y was e to the 3t. We're going to have then e to the x times y. So that's e to the t squared times e to the 3t, an exponential in the exponent, times cosine of yz. Well, yz is going to be e to the 3t times the natural log of t, times 2t, plus, I'm going to keep this in brackets, x is t squared, e to the xy, we said was e to the t squared times e to the 3t. Cosine of yz is again just cosine of e to the 3t times the natural log of t, minus, I'm going to move this bracket over, this is taking some space, z was the natural log of t times e to the xy was e to the t squared e to the 3t times sine of y times z is sine of e to the 3t times the natural log of t. And then that whole thing is multiplied by 3e to the 3t. Okay, just make sure I've got those brackets there. It would be optional to do the distribution of the 3 to the e to the 3t. If you want to, you certainly can, but not necessary. Okay. Minus y is e to the 3t, e to the xy is e to the t squared times e to the 3t, times sine of y times z was e to the 3t times the natural log of t, and all of that was times a 1 over t. Okay, holy cow, wow. Okay, now, that was a long formula, okay? But none of the work that we did was particularly difficult. A lot of it was just copying and plugging things in once we had them. Okay. And it may very well be that if we had actually written out the function composition here, we would have gotten a function of one variable, but there would have been so many rules that we were using. It might actually, in this case, be easier to use the chain rule for functions of one variable. I'm not sure. It's a complicated formula, but it was really just a question of being systematic and going one step at a time.